Hi, Haley.
Hey, how are you?
How are you?
Doing good.
Awesome.
Oh, Vanessa, hello, Haley, how are you?
Good.
Yeah, nice hearing it. Okay. Let me make you co-hosts. Vanessa, yes. Yes. Excuse me. So if anyone join, I'm not fresh enough. If someone tries to join, please help me accepting him or her. Oh, okay. Hello, Mara. Nice seeing you connected. Thank you all for making changes to the manuscript. I think everyone did it in time except maybe one, but I always have intention to reprint the booklet after the presentations with hello Hanman, nice seeing you connected, by including photographs like at the beginning of the presentation session. Highly likely you'll make a photograph and then include it into the booklet, but I'm not sure if, well, I will try to organize for printing a new version. If not, at least the electronic version can be shared with photographs. Okay. What I'm doing, I'm going to share slides. And it will be the same slide set that we considered yesterday. We'll just go over it completely. Okay. So we are in the computational chemistry course. It is the last lecture. The goal of the course was to provide some minimalistic theoretical background and get practical skills in running correct software on the right hardware and predict observables that can be compared to experiments, to other theories, and versus common sense analysis. And there is a component of scientific communication that includes writing mini papers and doing presentations and standing up questions of the audience. So we need to go to the DFT flowchart, and last time I will just go quickly through the slides because I think at least half of those who are today in the class saw the slide. So the goal of Td Dft is to predict absorption spectrum, and one is solving Cassidy equation to get transition densities and transition energies. So practically, one needs to add the keyword Td into the Gaussian input, and then it generates the .log file out of which one can parse the transition energies and oscillator strengths. There are a couple of simple scripts that allow to process the spectrum in the same style as we do in VASP, in single orbital in independent orbital approximation. So a column of transition energies and column of the oscillator strengths that can be converted into continuous distribution. Yeah, like is shown here. And this example of titanium hydroxide is a small molecule with a gap above visible, so it is transparent, which looks reasonable. The .log file includes information about each excited state. Excited states are composed of the transitions from one orbital to another one, but sometimes it is more than one orbital pairs. And the meaning of little numbers here and there, those are elements of the density matrix. Like for lowest transition, HOMO to LUMA, it will be this row HOMO to LUMA. It is not one because other pairs of orbitals also do contribute to the lowest transition, but in lesser extent. And Gaussian output is generated just for general idea. Okay, so we are seeing energies, oscillator strength that is computed based on trace operation out of the transition densities. And now it is time to revise which equation provides us these elements. So it is Mark Cassidy equation, which is formulated. So we have finished at this slide yesterday. So the theorems that are responsible for correctness of Td Dft, which we skip for the sake of time, do operate with an equation that looks similar to quantum equation for orbitals, but on the left side. But on the right side, instead of eigenstate, it is time dependence, right? Instead of eigenenergy and orbital, it is time dependence. And another thing that the potential is time dependent. So potential is time dependent because one assumes that the molecule is irradiated by periodically oscillating electromagnetic field. And there are ways to address this problematic. As we were discussing before, one does not solve it literally. One uses time-dependent perturbation theory. So the time Td Pt. So one is considering that in response to time-dependent changes of the potential, there is a first-order correction to the density, which includes pairs of orbitals appropriate for time for ground state unperturbed solution, and the pairs of density contribute to overall density with these coefficients change in the density, which are addressed as transition density. So the indices I and A here run only one index run from 0 to HOMO, another from LUMO to infinity. So one skips fully populated and fully unpopulated segments of density matrix because it would need higher orders of perturbation theory. And originally at first two lines we do have time, but in next lines the time is replaced to frequency by Fourier transform. So in this Fourier transformed response of density to oscillating electromagnetic field, one posing a question to find this transition densities and frequency. This is formulated in form of eigenvalue problem, where A index includes energy difference between independent orbitals and Coulomb attraction between electrons and holes and few other terms. this can be formulated either as functional derivative over, sometimes people use bigger delta, functional derivative of the potential over density, over this transition density, or it can be also formulated as second derivative of the total energy in response to density squared. The B term sometimes neglected even in practical computations, and it is called Tam-Dunkov approximation, Tam-M-Dunkov approximation, TDA. Sometimes if you do calculations and practical research with Td Dft, you will see it in the literature. Okay. So how does one implement this equation for solving? The elements of this transition density are saved in form of a vector. I think we already discussed it. And there is a iterative procedure performed in the language of flowchart, as we will consider here, and in any practical codes, one converts this algorithmic language into practical computation. So there is an idea of self-consistency. So one waits for arriving to convergence. So as an input, one provides similar parameters as one was doing in regular DFT. So positions of ions, number of electrons, tolerance. In addition, one needs to tell how many excited states one needs to get, because the larger the number of excited states, the longer the calculation. And if you are doing practical computation, you may see that it is very non-linear use of resources if you request more than, let's say, 100 or 200 transitions. Haley, would you like to confirm this statement?
Yes, that makes sense.
So how many excited states did you try in your research life?
For my smaller molecules, I do 100, but for the carbon nanotubes, I can only do like 8.
Okay, and can you share your feedback, your impressions of what would happen if you double the number of excited states? Would the time will be just twice as longer or much more escalating function?
It would take a lot longer.
Okay. So I wouldn't say right now from the top of the head, but at least the number of excited state to the power of third. So if you need a lot of them, it will substantially overuse your resources. And again, there, I'm making a little, yeah, thank you, Haley, making a little comment. Neither independent orbital spectra that we used for projects nor Td Dft are ideal in sense of precision. They both have errors. They all are approximate methods. There are much more reliable and in a sense of precision and accuracy. Right now, one considers the in chemical community EOMCC, and in the coupled equation of motion coupled clusters, and in physics community, there are several many body perturbation theory methods that are much more precise for computing spectra. Also, there is a quantum Monte Carlo that probably Hadassah have heard about from your advisor. But all precise, higher precision methods escalate numerical resources substantially. So even Td Dft, which is not by today is not considered the most expensive. It still may challenge your passions as humans. I want to say a little word in defense of independent orbital approximation that we are using for the projects. There are number of, so I'll tell something in this little corner. So in our independent orbital spectra in projects, you do have the file energy pop, energy underscore pop. And it just lists occupied and then unoccupied orbitals. So let's say M occupied and N unoccupied. So the total number of possible transitions of excited states in this basis will be M times N, right? Number of pairs. And if you have only 10 and 10 below and above, below HOMO and above LUMO, you already have 100 transitions. So you're already competing with Td Dft. If you have 100, if you have 100 occupied and 100 unoccupied, then number of excited states will be 10 to the power 4. So it will be amount of excited state and range of energies inaccessible for Td Dft in a reasonable time. So although we recognize that independent orbital approximation spectra are not sufficiently precise, they have some benefits. We can recklessly look for spectra in UV if needed, or we can treat systems with like couple thousand atoms and still get reasonable spectra. Okay, but now we do want to go over the algorithm for Td Dft. So the transition energies and the transition densities are improved iteratively, since the electron hole coupling in this A and B matrices does depend on functional derivative of potential over densities, over transition densities. The changes, updates to transition density affect the couplings. And therefore, there is a chance to cycle, to make an improvement self-consistent cycle for making this transition energies more accurate and more precise. So here's a little flow chart that we are going to view. So one starts from input, and as an output, one gets all requested transition energies from 1 to root, all corresponding transition densities. And in this diamonds, we need to have the conditions for transition energies falling into the tolerance limit. So what is going on? There are two cycles. So one cycle is for improvement of the transition energy number I, and another cycle is to go to the next transition. So in the inner cycle, one does solve Cassidy equation with best guess, the good guess, educated guess for the coupling supermatrices A and B. One uses solutions of this X and Y to compose the density, and then this density is used in the functional derivatives of the total second order functional derivative of the total energy to generate this coupling coefficients. And at the end of each cycle, one checks if the newly computed transition energy is worse or better, is converging with the value of this transition energy at previous iteration. If it is bigger than tolerance limit, then one uses newly computed couplings and resolves Cassidy equation once again, and then repeat cycle again. If the precision is achieved, then one can go into the next eigenstate, next transition number I, and then when the cycle is completed, there is an output that we already know how to process. Okay. So here is the same thing, just typed in better computerized calligraphy, and I believe we have approached the we have covered all materials that were planned to be covered in this course. So we started from molecular Hamiltonian. We spent a time to the most complicated thing, Born-Oppenheimer separation. I think it was and it is most challenging part of the course, and it is a good fundamental, especially to those of you who will look into theories rather than applications. Then we spent about a month on Hartree-Fock, another month on Td Dft ground state, and recently we have completed time-dependent density functional theory. So I have reasons to believe that everyone who went through the class knows how to independently build atomic models, optimize geometry, find simple observables like density of states, electron affinity, ionization energy, that right now we all know how to compute DFT in the independent orbital approximation by Td Dft. And also there is a skill of running and analyzing molecular dynamics. So we will finish the course in a few minutes. For academic part, tomorrow there will be presentations where everyone is expected to give 5 minutes summary of the research and stand the questions. Attendees are also very welcome to ask questions, but there will be guests, visitors who will set up their questions. What to do next? So next, you will get your grades, and at least we will keep friends for the rest of the life, and maybe you will use the skills towards your research and next courses. If you like this activity, if you want to continue research with these tools, the accounts and facilities will stay open. You're welcome to continue using them. And everyone who is volunteering and whose advisors are encouraging are welcome to visit group meetings of computational chemistry. They typically are arranged on Tuesdays, 4 p.m. in summer. So we will probably start at the last week of May. There will be no meetings for a couple of weeks, and the last week of May, Tuesdays, 4 p.m. And whoever is interested, I'll share the link. So there will be a program that repeats each year, and to some sense, it is a follow-up after this course. So at the beginning of the month, there will be several meetings where senior group members will provide overview of advanced skills. Skills that were not included into the course because they physically is not possible to squeeze them into 4-month course. And these advanced skills will be primarily related to predicting what happens to molecules in excited state, how they mechanism, how do they emit light. So not only to look on transition energies, but look on the mechanics and details of emitting light. Look on the details and mechanics of charge transfer, which is important. And also there will be chapter on chemical reactions. So it looks simple in these two words, but amount of skills is a little bit bigger. So it is doable, but challenging calculations. And after completing this knowledge transfer within maybe a month, there will be research presentations. So if there will be any volunteers to visit these meetings from the course, you have a chance to present your research from class in more details. Like instead of 5 minutes, you can speak for like hour and 2 hours, get constructive feedback, and make decision what to improve. And then summer will be over, and if anyone would like to keep staying in the fall, we will try converting all results into full-size papers to be published maybe by the end of the year. And in February, these papers are presented typically on Sunnybell conference, and then the life goes into next cycle with whoever takes the course next year. So feel free to consider. You all are welcome guests if you are interested. If no, I thank you all for enthusiastic contributions to all activities in the class. Wishing you good luck for last effort in completing your slides and presenting them tomorrow. And wishing you the best in all other classes and the progress, health and success in your research. Okay, course is done. Everyone is welcome to disconnect. If you have questions about the content of today's class or about tomorrow's presentation or about research, feel free to stay. I think we finished like 22 minutes before we were supposed to. So I'm at your disposal if you have any questions. But if you have your other things to do, feel free to disconnect. It's completely legitimate.
Thank you, Dr. Bina.
Thank you, Hemant.
Or Dr. Colleen.
Yes.
So I guess I'm for like this past semester, I've been attending your computational group meetings at Andre's recommendation to like start learning more background stuff. I guess so during the summer, I don't know yet what, or like if Andre's going to be like keep developing computational skills. So I guess I'll talk to him about that. But otherwise, would I still be invited or okay to participate in your research group meetings?
Oh yes, absolutely. So the plan for beginning of summer is as follows. So there will be about 3, maybe 4 weeks of knowledge transfer, and during this knowledge transfer session, everyone will refresh or just learn skills on computing electron phonon couplings and run electronic dynamics. Professor Krzyzewski does similar things by his own codes, but he's looking for electron phonon couplings as a response to distortion of normal modes, and he uses different, it's the same observables, but he uses slightly different equations for propagating electronic state in time. We are using on-the-fly couplings based on molecular dynamics. So the skill of molecular dynamics is a natural entrance and natural door to these advanced skills. And then upon couplings are computed, they are processed through several procedures and then the dynamics is computed by time-dependent density matrix approach. And then there is also a way to compute observables and compare to experiment. So if you stay on this path, it will add to your project from the class sufficient data to make it competitive and publishable. If you want to follow in all details the ideas of your advisor, you will need to learn skills that he solely possess on this campus, the skills of computing multiple exciton generation, so multi-electronic Coulomb integrals and dynamics with where the number of excitation changes along the timeline. Those things are complementary. You can try doing them in parallel or subsequently.
Okay.
Just a brief overview.
Thanks. I'll think about it, and I'll also talk with Andre. So,
Okay.
so
Very good.
All right.
Very good. Yeah, I will be very delighted to see you on these meetings if you decide to.
okay. Thank you.
Okay. Yeah. Thank you.
See you tomorrow.